Hello everyone, my name is Ian and today I would like to talk about a research on exploring the impact of switch Arity on flow control butterfly factory networks on chip for FPGA. Our claim is that compared to the state-of-the-art butterfly factory networks on chip based on Arity-2 switches, our Arity-4 BFT NOCs achieve 15 to 120% better ratios of throughput to LUT cost at the same data width, and for a given LUT budget, we shouldn't alter data width of switch links up to 88% higher throughput. In order to provide you with more context and motivation for this work, I would like to quickly address the three topics below, starting with why we consider overlay NoCs. So networks on chip are an important element in integrating subsystems nowadays, and in the FPGA context, this is made evident by Xilinx's new Versal architecture, which features a hard network on chip. While this hard NOC provides rich connectivity between processors, I/O, and the programmable logic, it only provides limited internal connectivity to the programmable logic, for instance between different accelerators instantiated in the reconfigurable fabric. It should thus be complemented by an overlay NOC, which provides this missing last mile connectivity, aiming for minimal LUT footprint and maximal throughput. With this in mind, we may compare different options for overlay networks on chip in terms of footprint, throughput, in-order delivery of packets, freedom from livelocks, and adaptability to application bandwidth requirements. On one extreme of the spectrum of options, we have designs which use deflection to deal with contention for switch ports, such as Hoplite, which has a torus topology, and the butterfly factory option. These designs achieve low footprints, relatively high throughputs, but lack important features. On the other end of the spectrum, we have CMU Connect, which has complex buffer switches. It achieves a high throughput and a rich set of features at the expense of having a large footprint. Xilinx's AXI-S interconnect has a low maximum throughput and is thus not appropriated for high throughput designs. Our work builds upon Arity-2 butterfly factory NOCs with flow control, which have intermediate footprint and the highest throughput among the options considered, while also achieving the three features under consideration. The Arity-4 BFT NOC have lower footprint compared to Arity-2 BFT NOC, but also lower throughput. It also makes sense to consider the rate of throughput to footprint, and in this case, the Arity-4 BFT NOC achieved the highest ratio among the designs, which also achieve the three important features under consideration. We now quickly introduce the Arity-2 butterfly factory NOCs with flow control, which we build upon. So the Arity-2 BFT NOCs are hierarchical structures where the network clients are present at the bottom of the hierarchy and are connected by layers of pi and T switches, where pi switches have two bidirectional links facing downwards in the hierarchy and two links facing upwards, while T switches have only one link facing upwards. Packets are routed from source to destination by climbing the tree hierarchy until arriving at a switch from which they may descend to the destination. A later work added a latency-insensitive interface to implement flow control, where packets that lose contention for switch outputs are stored in shadow registers. A round-robin arbiter ensures fair access to outputs by inputs. Now we consider why it makes sense to explore Arity-4 BFT NOCs. So here on the right we have the three Arity-4 switches we have defined. We observe that they naturally have more ports than the equivalent set of Arity-2 switches. This larger number of ports implies that wider multiplexers are needed internally, but this presents an opportunity to harness mechanisms for implemented wide multiplexers efficiently offered by modern devices, such as the F7 NOCs present in Xilinx's Series 7 FPGAs. Arity-4 BFT NOC have lower total numbers of switches and of switch ports compared to Arity-2 BFT NOC with same bisection bandwidth, and this implies a reduced overhead due, for instance, to buffering of packets in switch inputs. On the other hand, Arity-4 switches have more complex arbitration and deeper multiplexers, which results in a frequency penalty. Here we have an Arity-4 BFT NOC with the bisection bandwidth of a tree, and by selecting the switches used to compose layers of the tree hierarchy, we might construct BFT NOC with the bisection bandwidth of a mesh, with a rent parameter of 2/3, and with the bisection bandwidth of a crossbar. In terms of results, we first synthesize the Arity-4 BFT NOC to the Xilinx VU9P FPGA, as well as Arity-2 BFT NOC, and verified that the Arity-4 BFT NOC consumed 38 to 45% fewer LUTs in exchange of a reduction of maximal clock frequency in up to 25%. Here we explore the throughput achieved in bits per nanosecond, achieved by Arity-2 and Arity-4 BFT NOC, when routing packets between 16 network clients. The data points correspond to different width of switch data links, varying from 32 to 512, and we see that the throughput of Arity-4 BFT NOCs scales much more efficiently with the increasing cost of increased data weight of links in comparison to Arity-2 BFT NOC, both when using shadow registers to store packets or when using SRL FIFOs. Here we plotted the ratio of throughput to LUT cost achieved by BFT NOC with Arity-2 and Arity-4 when routing network traces derived from sparse matrix vector multiplication benchmarks, and verify that Arity-4 BFT NOC achieve ratios 15 to 100% better than equivalent Arity-2 BFT NOC with same bisection bandwidth. We invite you to visit our public Git repository, which contains RTL code for the Arity-4 BFT NOC, as well as associated scripts for running synthesis and simulation experiments.